All right, let's talk about conservation of momentum. Momentum, like energy, is a conserved quantity in a closed system. When there's some sort of process or interaction, the total vector sum of the momentum before this process equals the total vector sum of the momentum of all the objects in the system after that process. So I said vector sum. This is a big difference between momentum and energy in terms of their conservation. Energy is a scalar quantity, momentum is a vector quantity. So we do need to keep track of components if we're working in 2 or 3 dimensions, and if we're doing a one-dimensional problem, we have to keep track of plus and minus signs. So the law of conservation of momentum can be written quite simply as the sum of all the momenta in the initial state of a system equals the sum of all the momenta in the final state of the system. In most of the problems we do in Physics 6, there's just going to be 2 or even 1 objects that make up the system. So it'll usually just be like 2 terms in the beginning and 2 terms at the end. But in principle, this works for systems with lots of objects, many objects or particles or something. And we're especially interested in analyzing collisions. Now, in daily life, when we say collision, we're thinking of 2 macroscopic objects coming in direct contact with one another. They're colliding with a contact force. But collisions in physics are actually more general than that. You can have collisions without direct contact between objects, especially when you're getting into subatomic particles. In particle accelerators, you study collisions between particles, but particles collide or interact via the electric force or a nuclear force, and so they're not coming into direct physical contact in the same way that we think of it in everyday life. In fact, in everyday life, when 2 objects come in direct physical contact, what they're actually doing is interacting via the electric force. If you looked microscopically at my hands colliding, they wouldn't ever be touching. They would be repelling one another. The electrons in one hand would be repelling the electrons in the other hand via the electric force. So imagine we have 2 objects that are going to collide, object 1 and object 2. There's the initial state of the system, they're heading towards each other, and then the final state of the system, maybe they bounce off one another. There's a lot of different possibilities for how that collision could occur. But I just wanted to point out that during a collision, Newton's 3rd law is still true. Newton's 3rd law is always true. And during a collision, it's enlightening to think about what's going on in terms of Newton's 3rd law. When these 2 objects begin to collide, object 1 is applying a force on object 2. And that force is pointing to the right. So it'll be positive in this graph. It starts out small, it gets bigger, then the objects start moving away, and that force gets smaller. So here's a graph of the force of object 1 acting on object 2. Newton's 3rd law says that the force of object 2 on object 1 is exactly the same magnitude just the opposite direction. So during this collision, object 2 is pushing to the left on object 1 with the same magnitude of force. My drawing skills aren't perfect, but the idea here is that F2-1 is supposed to look exactly the same as F1-2, just negative. This is a consequence of Newton's third law. All right, let's think of a few examples of momentum conservation. I'll do two kind of qualitative examples and then one calculation. First example is a squid. So the way that squids swim through the water is that they suck in some water to their bodies and then spray it behind them like a jet. And the reason why they get propelled forward is because you can imagine, say a squid is stationary, it has some water inside its body, and now it pushes some water out. That water now has momentum going this way. In order for the total momentum of that squid water system to be conserved, the squid must then acquire an equal amount of momentum the opposite way, so that the total momentum equals 0, the initial momentum of the squid water system. Second example is what happens when you jump off the ground. Before the jump, your momentum is 0. Immediately after the jump, you have some momentum going upward. So it might seem like momentum's not conserved, but you have to consider the whole system, which consists of you and planet Earth that you're pushing against. When you jump up, you are pushing the Earth down. So in fact, if there's 0 momentum to begin with, and then you jump, you have upward momentum, but then the Earth acquires momentum in the opposite direction. It's exactly the same amount of momentum that you have going up, so that the total equals 0. So both of these examples are kind of related to Newton's third law. They're related to conservation of momentum, and they're related to Newton's third law. Because you have to have something to push against in order to move. A squid is able to swim because it's pushing against water it shoots out of its body. The squid applies a force that way to the water. By Newton's third law, the water applies a force of equal magnitude in the opposite direction to the squid, so it moves. The ejected water has momentum going this way, the squid acquires momentum going the opposite direction. When you jump, you apply a force downward on the Earth. The Earth applies a Newton's third law force pair upward on you. You acquire upward momentum, the Earth acquires downward momentum. Let's do a quantitative example. This is example 6.3 from your textbook. You have an archer, someone who's shooting a bow and arrow. The archer's standing on a frictionless surface like ice. Probably not the greatest thing to do if you're an archer, but this is a textbook, so it makes sense in the textbook. And we want to find out what happens after the archer shoots an arrow. So the idea is if you shoot an arrow, you initially have zero momentum for the system. Now you let the arrow go, it has momentum going that way. And so you get a recoil. You acquire momentum going the opposite direction. So here's the given information, the mass of the system, the archer plus the quiver of arrows is 60 kilograms. The mass of an arrow is 0.03 kilograms. We'll call that M2, that's the arrow. And the arrow gets shot with a velocity of 50 meters per second going to the right. So the first question we can ask is, what is the archer's final velocity after shooting this arrow? So let's call that V1 final. The archer's mass, we'll say, is M1. We can figure this out using conservation of momentum. So the law of conservation of momentum says that the total initial momentum equals the total final momentum. So let's write this down really clearly. Initially, the archer is just standing there with the bag of arrows, quiver of arrows. That's going to be 0. And then the archer shoots the arrow, and now the archer is moving with their own velocity, and the arrow is moving with its own velocity. So that's 0 because everything was stationary to begin with. And now we can do a little bit of algebra and solve for V1 final. Now there's just one slightly tricky thing to keep in mind. It's that the archer's mass is the total mass minus the mass of the one arrow they shot. So this becomes M2 V2 final over M total minus M2. That's to account for the arrow that just flew away. And when you put in all these numbers, the archer is now moving backwards. Moving in the opposite direction that the arrow is moving in. So there's a recoil. When you shoot an arrow, the arrow goes that way, and you get pushed the opposite direction because it's the same thing as a squid shooting water out behind them. It's the same thing as, well, not really the same thing, but kind of similar to jumping off the ground. You're pushing the earth away from you. That sends you moving upward. So you're shooting an arrow out from you that sends you moving backwards a little bit. All right, let's answer some more questions about this archer situation. What happens if the archer fires a second arrow? And that arrow is at an angle. .30 degrees above the horizontal. So the archer's already moving backwards a little bit, and now they're going to fire another arrow. So let's write down this setup here, and we'll also have to account for this angle. So once again, the setup is that we have the mass of the archer, which was m total minus m2 times that v1 final from the previous part of the problem. And now they shoot another arrow. So we've got m total minus 2 arrows now. And let's just call the answer to this part V. I'm running out of labels. That's what we're going to be looking for. And we've got another arrow flying off at M2, V2 final, but it's going at an angle, so we need the cosine. That turns into a bit of an algebra party. You can go ahead and try to solve that algebra, and you'll find that this final recoil of the archer is now 0.467 meters per second. Makes sense, they're recoiling even faster now because they already got going from that first arrow, now they shot another one. Notice this recoil isn't, it's not exactly twice as fast as this because this thing is happening at an angle and the person's also losing mass. But it's nearly twice that value because they've shot 2 arrows.